Hello, hello. Okay, so we're gonna go ahead and do the worksheets for today. You have two, you have 3.1, 3.2. Let's get started. So remember, vocabulary increases means positive and decreases negative. Constants are, well, they're just constants, right? Okay. Rectangulars. Ooh, I'm tired. Okay. Sorry. A rectangle's length increases at 4 meters per second and width decreases at 1 meter per second. How fast is the area changing when L is 12 and W is 5? Okay, so rectangle's length, so we're literally just measuring just an area. So let's go ahead and just put the area function. The area of a rectangle is length times width. And then when you do the derivatives of all this, so we have derivative of A dt is equal to derivative of L dt times W plus L times dW times dt. Okay. So they want to know how fast the area is changing. So not the area, but how fast it's changing. So they want to know dA over dt. So this is probably just going to be a plug and play. Let's say this number one says the rectangle length increases at a rate of 4 meters per second. So we're going to plug in that 4 here. And it says the width decreases at a rate of 1 meter per second. So that means we're going to include that here because they're both rates. And then it says L is equal to 12 and W is equal to 5. So we're just going to plug in those numbers. We have 4 times 5 plus 12 times a negative 1. Now it's negative because it says decreases. So there's a hidden negative in there. So 20 minus 12, that's going to be 8. So my answer of how fast the area changing is 8. Is 8, what is it, meters? Yeah, 8 meters per second. All right, 2. The volume of sphere increases at 20 cubic meters per second. How fast is the rate increasing when R is equal to 2 meters? Okay. So volume of a sphere, V is equal to 4 over 3 pi r squared. The derivative, r cubed. Derivative of this is dv over dr, and t, excuse me, is equal to 4 over 3 pi 3r squared times dr over dt. Let me clean that up just a bit. 4 pi r squared dr over dt. Okay. All right. The volume of the sphere increases at 20 meters per second. So that means we're replacing that derivative of v with 20. How fast is the radius increasing? So the fast and increasing implies that we want to solve for dr over dt. And then they just write what the radius is. Radius is 2. So we have 20 is equal to 4 times pi times 2 squared times dr over dt. Let me go ahead and just divide out the 4 since I see that right away. It's 5 times pi over 3 pi over pi times 2 squared times dr over dt. That square is just 4. I'm going to divide. All right, so 5 over pi 4, or 4 pi to dr over dt. And that's going to be your answer. Right. Next, a rectangle has a constant area. Its length is increasing at 2 meters per second. How fast is the width changing when the length is 10 and the width is 5? Okay. So let's go ahead and copy and paste the formula. dw over dt. And let's read this from left to right. Okay, so the first thing, a rectangular has a constant area. So this is almost a trick phrasing. That means that the area is constant, it doesn't change. So what's the derivative of a constant function? It's going to be 0. Its length is increasing at 2 meters per second. How fast is the width changing? So that means we want dw over dt. When the length is 10 and the width is 5. So let's plug this all in. We got 0 is equal to 2 times 5 plus dw over dt times 10. Okay. So that's going to be, to simplify this a little bit, dw over dt times 10 is equal to negative 10, which we can see that dw over dt is just negative 1. So you can either say it's increasing at a rate of negative 1 meter per second, but you're clearly better off saying that the rate is decreasing at a rate of 1 meter per second. A spherical balloon deflates, so its volume decreases at 12 cubic meters per minute. How fast is the rate changing when r is equal to 3? Okay, so we're dealing with spheres again, so I'm just going to copy and paste that formula. dv over dt is equal to 4 pi r squared dr over dt. Reading this from left to right, it says the volume deflates, so its volume decreases at a rate of 12 cubic meters per minute. So I think we're dealing with that. How fast is the radius changing when the radius is slowing? So we're going to do negative 12 is equal to 4 times pi times 3 squared times dr over dt. Well, I know this is just an extra 3 with 12, so I'm going to go ahead and factor that out. We got negative 1 is equal to 3 pi times dr over dt, and then just solve for dr over dt. Negative 1 over 3 pi. So the radius is decreasing at a rate of 1 over 3 pi. All right, that's pretty much it for these. Let's wrap this up with the last worksheet. The derivative of unknown function, or this is the derivative of unknown function. Use it to find and classify all of the relative extrema. So we have the derivative of x is equal to x squared times x plus 2 times x minus 3. Okay. Nothing too crazy, but we tentatively have just derivative provided to us, which is a little weird, but nothing we cannot handle. So let's go ahead and simply just solve for when this is equal to 0, which is already factored for us. So we can say we just have x squared is equal to 0, x plus 2 is equal to 0, and x minus 3 is equal to 0. X squared is equal to 0 means that just x was equal to 0. X plus 2 is equal to 0 means x is equal to negative 2. And x minus 3 is equal to 0 means x is equal to 3. So that means we have 3 critical points. We have negative 2, 0, and 3. So we need to pick easy points that's in between these guys. Let's just go in on the outsides. So let's just do negative 3, negative 1, 1, and then 4. And we have x squared, x plus 2, and x minus 3 to evaluate for these guys. Okay. So we know for squares, it'll be positive no matter what. So all these signs are positive. And then for x plus 2, we'll have a negative here, positive here, positive here, positive here. X minus 3, we'll have a negative here. We'll also have a negative here. We will also have a negative here, and then we'll have a positive here. Okay. So then we can go ahead and get the whole function sign, which here it'll be positive, here it'll be negative, here it'll be negative again, and then here it'll be positive. So that means that we at -2, it went from positive to negative. So it went up and then down. So that means that -2 will be a relative max. And x is equal to -2. It's not done though. We can still have more technically. From 0, it went from negative to negative. So it's not either a max or a min. And then for 3, it went from negative to positive. So it rose. So that means that at 3, we have a relative minimum at x equals to 3. And that's your answer for these. Now, technically speaking, we can go ahead and get not the best idea, but an interesting idea in all these. Using information from question 1, draw an example of what an original function could look like. Remember that the first derivative tells us the slope of the original function. So we know that at x is equal to 3, we'll have some kind of dip. And x equal to 2, -2, so we'll have some kind of max. So from -2, we technically, towards the left, it was a positive value. So that means it increasing. So it was going upwards all the way up till that -2, where it started going downwards. And even though at x equal to 0, it's a critical value, it's not really saying that it shifted. Maybe it shifted trajectory, maybe it became steeper or became, less steep, but it still just technically implies that it just passes through there. So it's actually going to keep going down. But then at 3, it goes up from negative slope to a positive slope. Now, again, this is one of those problems like what we talked about with the mean value theorem, where this picture doesn't have to doesn't have to match exactly my picture, but it is that sort of like we should see some kind of similarity. There should at least be this little hill and this little valley. All right, that's gonna wrap it up for today, guys. Let me know if you have any questions, and I'll see you all in the next one. Bye bye.